Okay, welcome. Let's get started. So today we're going to pick up from Wednesday's lecture talking about cache coherence. But before we do that, I did want to do a 5-minute demo of how to compile for ESESC for your project. Some people were asking, why can't my random binary work for on ESESC? And so to do like a really quick demo, I can maybe clear it up. Right? So to run on ESESC, you need two things in your program. Number one is you compile for RISC-V, and number two, you need to be statically linked. Right? So you need to do both of those things. The easiest way to do that is to get a hold of your source code and to get the RISC-V GCC cross compiler. So there's actually two, and both will work. So they're already installed in this machine I'm on right now. Make that bigger still. Is that more readable? Yeah. Okay. So there are two. As I said, why is that not autocomplete? Oh, 64. Okay, so there's the one is newlib based, which is this one, and then there's the one that is glibc based. I'd recommend the first one, the newlib one. However, if you use apt-get to install these tools, you're probably going to get the second one, and that's also fine. So two different compilers. So why don't I do examples? Let's say, in this case, I already have ESESC downloaded, and they've already built it. In this case, I actually built it inside the source directory. You aren't supposed to do, but we already built it. And so I'm going to make a new directory for running. And let's just make it write a little hello world so I can write this out very quickly. Okay. All right, we're going to close this up. Great. So oops, I got the wrong combination. There we go. Oops. All right, great. So I have that. I need to compile it. So as I said, there's two ways to do it. One is with the newlib, which I'm going to do first. So that one's not too complicated. Just got to use that compiler. Because it's C++, I'm using G++. I'm tossing those three because why not? And then I'm going to give it a name. So this is like using GCC normally, just now I have this binary because it's compiled for RISC-V. If I try to run it on this machine, which is x86, of course it's going to be unhappy because it's not the right ISA. But if I want to run on ESESC, I'll do that right now. And so because first I'm going to need to copy the configurations, right? And so I'm just going to copy them in here. And then for the ultimate in expediency, I'm not going to actually change the configuration file. I'm just going to use an environment variable. So I'm going to tell it the thing it's running is this hello.rv. And then, of course, going to need the path to the compiled ESESC, which in this case, I believe I can just sneak back this way. Yep. So it ran. And so we see hello. Great. And now if I run, I should be able to see data right now, right? Yep. It's a little bit hard to see because the print's so big, but it did run a few instructions. Great, because it's a hello world. You can see these are all non-zero. Okay, and so I could also, so that was using newlib. So that one, if you can get that compiler, it's pretty straightforward. Looks just like GCC, just happens to compile from x86 to RISC-V. If you use the glibc compiler, the one that's called Linux, it's going to look pretty similar. So I'm just going to modify this command a little bit. So it's still unknown, but now it's going to be Linux, still G++, but now the keyword is static. And I'll mark this one as different, just because that way we can tell them apart. OK, so Now I've statically linked that one. So the newlib one is by default static, that's why I recommend it. The glibc one is not. You have to tell it to go statically linked. And then we run it similarly. So I have to just tell it this right here. You can see in the middle here, does it ran? We can also do a report on it. So I didn't tell you this until now because, of course, you didn't need this for the lab. You only needed this for the project. Questions? Go ahead.
How many instructions we have to run for the project? I mean, the number of, for lab we had 7 billion instructions, right? So how many instructions should we set for?
So that's a great question. So for the project, I'm not specifying a exact instruction count. It's more for you to demonstrate the goals of the project. Demonstrate the goals of the project are to have found a workload which is bottlenecked, to demonstrate you identified the bottleneck, both through your measurements initially as well as your intervention, which changes the architecture in a way that ameliorates the bottleneck, right? So it's kind of up to your project and the context of where's your workload to make that work out, right? So we gave you a range for instructions we wanted for the project, so that way it would be easier to have a reasonable runtime. But yes, depending on the sampling parameters, it can vary. I would probably, for your final runs for your project, increase the number of instructions max up a little higher. But I mean, you don't need to go too high because the specifications tell you not to go above 10 billion instructions, so it's not that much higher. But if you want to, for example, decrease the rabbit to get a higher fidelity result, that's also an option. Yeah, good question. So I know this was pretty quick, and so I did have a slide that summarizes this in the very first of the lecture, which is not showing up. Oh, there we go. Great. Perfect. Yeah, so this is showing that right here for future reference. So depending on what OS you are, you should just Google for, RISC-V cross-compiler. For this part of the project, you don't necessarily need to use the VM if you don't want to. The nice part of the VM was a way for us to distribute the benchmarks. But if you do use the VM, I believe RISC-V GCC should be inside there. I'm looking at the TA for a nod. Is that true? TA's not here. OK. But I believe that should be in there. So that should already be in there. You should already have the cross-compiler available within the VM. If not, we can probably post a new VM in a few days to make sure that's the case. Other questions? Yeah.
My understanding is we can't do perf in a VM.
Correct. Yeah, so for those who are wondering about what would I do if I don't have perf handy, number one thing you're trying to do is trying to find the workload, right? So for any given platform you're on, there's other ways to measure IPC without perf. Perf is just the best tool for Linux, right? So you might as well find the workload first, and then borrow a friend's computer one time to get the perf numbers. That's harder for you to do. The goal for this project, of course, was that given 10 weeks, at some point you can find your way across the machine with a perf to do that part of the project. And for those of you who don't have Linux by default, like me right here, the recommended thing to do is to install Ubuntu on a flash stick, and then that way you can dual boot, not by changing your internal computer, but by putting it on the flash stick, and you can drive Ubuntu, for 1 hour, one time on the flash drive to get the needed numbers.
I don't believe you can do that on the newer Macs.
You can.
You can?
You can definitely run Linux on a new Macs.
I thought the secure boot blocked you from doing that now.
You should disable it, right?
You can't disable it on the newer Macs. Anything post 2018, I think, is...
Okay, you're right. I've not tried it since the 2016 Mac, so I don't have a 2018 Mac. I only have a 2016 Mac. Okay, I can't say for that. Okay, in that case, I can't say. But usually there's a way to override these secure boot things.
They used to be.
It used to be, yeah.
So you're saying your 2018 ones can't do this?
Not after this. Once they added the T2 secure chip, they blocked all of that out.
Yeah, they added a new chip.
Okay, well, in that special case, you might consider the machine you had prior to 2018 MacBook Pro. What? Yeah, so you students will probably know better than I will about which labs are available for what. The dance machines, which are for login use by grad students, unfortunately, I believe are VMs that don't have perf available, right? Someone can correct me on that one. But if there's other machines you can use perf on, that'd be great. And that would be most appreciated if you could post that in the news group for others to see.
Question? So does this VM then have perfs in it? I mean,
Oh, the problem is perf needs to access performance counters, and so most VMs block those. That's the issue. The one exception to that is Docker, which is not quite a VM, it's like a VM. In some cases, when Docker is running on a Linux host, you can use performance counters. But that's the only exception. For the most part, you usually can't use performance counters inside a virtualized environment. The point of the perf in the beginning of the workload is mostly just, it's going to be much faster for you to compile a workload and evaluate with perf than for you to compile it for ESESC and run with ESESCify and IPC, right? So for that search period, where you're trying to find a workload, that'll be faster. That's the reason why that's ordered in that way.
But all we need is an IPC.
And some preliminary measurements to identify the bottleneck, which you could do in a couple runs of perf, right? So perf is a command where you can give it, arbitrary performance counters you want to track, right? And so, you're going to run it once, get a low IPC, and you say, oh, I think, I'm perhaps limited by, branch mispredictions. Okay, I'm going to measure the branch mispredictions on with perf and show them being problematic. Then when you recompile that same code for ESESC, you run on ESESC and show an ESESC report, this simulation's reproducing the same circumstances and also has a problem with branch mispredictions. And then somehow in your project, you're going to propose, well, what changes should I make to the branch prediction parameters to make this fixed, right? So the point of this workload is kind of to model a scenario that's most likely to happen for most of you beyond this course, where you're going to have a workload, you're going to want it to go faster, you aren't quite sure what the problem is, you need to find the problem, and changing parameters in ESESC is the way to demonstrate you've identified a problem by showing you fixed it. That's kind of the storyline for the project. Okay. In that case, we'll actually get back to cache coherence. So I'm talking about parallelism, talking about TLP. So we saw this messy protocol last Wednesday. So I did want to do one more example. Actually, in this case, I should go back a slide. This one, the point of this example is to show that here in this system, you can see that we have multiple buses, right? So just because we're doing snooping doesn't mean we can't partition our network. It just means the domain for which snooping is, that's the coherence is applied is within that one domain. So for example, here you'll notice that there's a bus between the L1 and the L2, but this bus does not include this L1. To make this more clear, right, there's connections here like this, right? So we can kind of see which things are connected to which. So for example, by now, so each of these different levels will then be running kind of, each of these buses will run coherence in that bus. So for example, starting off, let's say we're doing this load, and we have a miss. Okay, well, what are we going to put here? We're going to put a read request, right? Because it's a miss, and we're only doing a read. So we're going to put out a read request, and then we're going to, it's going to go out on that bus. It's going to get to the L2. The L2 is going to look for that data. Let's say, for now, it's also not in the L2. So then the L2 is going to propagate the read request. It's going to go out on this other bus, and nobody else is going to respond. At least this guy's not going to respond. So it's going to, be absorbed by memory and then work its way back. And so it's actually going to go into the L2 in E, right? And it's going in E because nobody responded saying they already have this in the sharing state, right? It's also going to come back into the L1 in E as it, works its way all the way back. So we can see now that this cache line is in the L2 and the L1. We're assuming they're inclusive. Great. So now we're going to do the store. And so at that store, what's going to happen? Well, we're going to check for it. It's going to get a miss here. So it's going to put out on this bus, hey, I need a exclusive access because I want to do a write. So I'm going to put out a request for that. And no one's going to respond. Sorry, it's going to go out on this bus. And now this one's going to respond, oh, wait. It's already in the E state for the other core, or for another core in the system, so it's going to respond, put this into M, and send in the validation this way, back up, right? So eventually it's going to get this, and it's going to go to M, and we're able to go from E to M here, of course. That's one of the messy allowed transitions. And so that didn't require any other intervention. Now if we do the final load, what's going to happen? Well, it's going to check here. It's going to be a miss. So it's going to send out that read request. That L2 doesn't have it, so it's not even going to respond. It's going to get forwarded again. And now this time around, this read request goes out. And remember, in case we forgot from last time, OK, well, if I'm in M and someone, oops. Well, give me a second. This projector's not on. Oops, that's not the right one. Give me a second to safely launch my freaking remote software. Okay. I think now it should work, hopefully. OK, so yeah, so if we were in the M state and someone we receive someone else asking for a read, another processor reads, we have to write it back to memory, but then we're going to go to shared, right? So we're going to see that going by. We're going to go to shared, but we're also going to write back the data. Now, there's one little detail, and of course this is eventually going to work its way to shared. This cache didn't necessarily have the dirty data, right? The dirty data was in the L1. And so it may have had to request, so it would have had to also have sent the write back request to the L1 in order to get the data to come all the way down here, right? Because the L2, if this is a write back, not a write through cache, wouldn't necessarily have had the most recent dirty data. And so it is important for it to propagate that message all the way through to come back out. Question?
So the L1 cache will have it as in the shared state then?
Which one? Oh, sorry, at the end, this will transition to shared, yes. Yeah, exactly. Yes, that also will get a great point. It'll also be populated there. Yes. Yeah, so when data comes back around, it's going to go to both, correct. If we have an inclusive design in this case. OK, so that was this example. From last time, we had this false sharing, true sharing slide. I actually took time to consult the original creator of the slide, as well as the textbook, which they were inspired by from the slide. And I have modified the slide in the way I think is most explainable. So, OK, so we have two different words, x1 and x2, but they happen to be in the same cache line. And so we're asking, whether it's true or false sharing. So remember, true sharing is when it's the same word, and false sharing, it's different words, but happen to be in the same cache line. So initially, they both had the data. They have that one cache line, and it's in the shared state. So now if P1 performs a write to one of those words, it's going to have to send that in validation to the other core to remove that cache line from the shared state. So you might want to call this a miss, but depending on the protocol you have, maybe a better word to call this is an upgrade, right? Because you already have the data. There's no reason for you to toss it out and then request it from memory again. You're just upgrading the permissions you have for that cache line. So for the sake of what's actually happening, we're not moving any extra data. We're actually doing an upgrade. But we are going to invalidate the data in P2 because it's the same cache line. Now, when P2 wants to read X2, X2 was in its cache. But the reason why it's not there anymore is it just had that cache line yanked out by an invalidation, right? So this is the false miss. This is the false one we don't like because X1 and X2 are different words. P2 doesn't care about X1. But because X1 and X2 happen to be in the same cache line, that's why it got invalidated. And so as a consequence of reading X2, it's going to trigger more transactions. It's going to go from invalid to shared. And because it's going to shared, it's going to force P1 to go from modified, do its write back, and into shared. OK, but then now in step 3, when P1 does a write, we're going to see something similar, right? Where P1 has data, but it's in a shared state. It needs to get to the M state. So I'm using, once again, this upgrade in parentheses to imply that it's actually not moving the data. It's just requesting additional permissions, but it's still causing transactions. In this case, P1's annoyed because it doesn't care about X2. And the reason why, even though it had this data in the M state and it's not in the M state anymore, is because because P2 wrote to X2 is a different word. So it's a false. And then, of course, now as a reminder, it's modified for P1 and valid for P2. Now, if P2 does a write, same thing. X2 and X1 are different words, so it's still false. Because we were formerly invalid and validated data, it's actually true. It's actually a miss. It's actually bringing the thing in, but it's false because they're different words. And now, finally, if P1 actually reads X2, that's actually a true miss, right? Because it actually is the same word, right? There actually is sharing or communication happening there. So they will need to copy it over.
Could you go over that again?
Could you give maybe a more specific question or part?
Could you draw it so you could actually draw in where the I is and where the
OK, so right. So for this one, for time, we have 1, 2, 3, 4, and 5. P1 and P2, right? And actually, I'll squeeze in 0, right? And then if I start filling in the values, right? Initially, they're both shared. Then what happens? Well, the first one writes, and so it's going to validate the second one. Then the second one reads, so they both get migrated to shared. Then this one writes, and so it's going to knock the other one back down again. This other one wants to write, so it now is going to change it over. And then finally, they're both going to be shared.
Okay, thank you.
No problem.
That helps a lot.
Yeah, I think the slide can keep being iterated on. So this is good feedback. Good. OK, so how might this actually play out in practice? So there's this famous study from about now 15 years ago running on some DEC alphas where they really carefully measured what are the sources of every cache miss in the system, and they varied system parameters. And so what's happening? Well, they're running a multiprocessor workload. It's an online transaction processing, L2P database. But the key thing is we're just going to be kind of playing with these processor parameters, right? And so we're classifying our memory cycles based on a few types, right? So some are due to, of course, fetching instructions. The cache miss is due to that kind of delay. This particular workload is not able to disentangle the difference between capacity misses from conflict misses, but they're both shown. Of course, our cold or compulsory misses. But then the coherence-related misses that force C are shown by both true sharing and false sharing. So now, this is already running on 4 cores, and the workload is running across those 4 cores. So what are we going to do? We're going to increase the size of the cache from 1 megabytes to 8 megabytes. So what we're going to see is that the conventional cache misses, especially ones from uniprocessors, are going to be improved, right? You have a larger cache, we have more capacity, things are going to get better, right? So the impact of instruction misses is going to go away. Notice it's going to get smaller. The conflict compulsory is going to get smaller, but we see that the sharing misses are basically unchanged, right? We see, and of course, the reason why is that these misses are not due to cache size; they're due to actual communication between these threads, right? And of course, with true sharing, we actually intend for data to be communicated, and with false sharing, it's a byproduct of doing coherence on the granularity of a cache line. So kind of see this another angle. Now we're going to scale this workload up, and so it's the same types spots for these bars. And now going from 1 core to 8 cores, we see that we're actually going to increase our AMAT, right, or average memory cycles per instruction, right? Because what's going to happen is, with 1 core, we have none of these coherence misses. But as we add more cores, we're going to increase the number of coherence misses. And so what we're also going to see is that, of course, both true and false sharing increase. But in general, the coherence misses go up with more cores.
So the instruction category here, that's because it's a shared cache, is that right?
No, they each have their own caches.
And then IMD is the same cache.
At this level, they're the same. This work has a tiny L1 instruction and data caches, and this is a L2 cache per core we're talking about. Yes.
So if we were thinking about a pure data cache, the instruction component wouldn't come into it.
Correct. Yeah. So instruction cache miss is something I've not spent a lot of time in this course on, but they're actually really problematic in practice. Your high-performance math kernels tend to have very small code sizes. Almost everything else tends to have really big code sizes, and making sure your processor instruction executes a really important bottleneck. And this has become, I would argue, maybe the most challenging microarchitectural challenge within 1 core right now. Or if you ask someone from Google what do they most want them to fix about single core performance, instruction fetch from caches is their top request. The reason why is for these data center workloads, they have instruction binaries in order of 1 to 4 gigabytes. A 1 to 4 gigabyte binary is not going to be friendly to a 24 megabyte last level cache. And so if you have to go to memory to fetch instructions on a frequent basis, that's going to completely throttle your performance. So as a research topic, people are all scratching their heads on that one. It's a hard problem. We're not really sure what to do about it. But yeah, so this wasn't just a Google problem now. It was already this problem on the horizon for a few years. In this case, this is a 10-year-old, 15-year-old study, but even in those OLTP workloads, they were starting to already have this problem of having very large binaries with poor instruction reuse, and thus they had these instruction fetch issues. But for this course, I mostly emphasize data caches. This is correct. But I guess for your own general knowledge, it's important to be aware instruction misses are also very problematic at times. Okay, well, next let's get to the question people kind of always been asking about, and that is, well, gee, this shared bus we have on these systems doesn't seem very scalable, right? And if you think about that, right, every time you want to add more cores to the same snooping domain, that means the bus needs to be made bigger, so that's harder electrically to do that kind of stuff. But additionally, that means there's going to be more traffic generated, right? So at some point, your bus has a finite bandwidth. You may actually saturate the bandwidth on your bus to everybody communicate about things, and realize all these transactions on a snooping bus, everybody who's part of these buses has to be checking their own caches, right? So for example, when this request goes down here, even though this cache is invalid, it needs to check its tags to know it's invalid at that point earlier on in the workload, right? And so there's a lot of kind of wear on these caches. And the point is that, for the most part, most requests are not going to be to contentious data, and so they're not really going to need to have coherence. And so you're kind of really doing a lot of work, kind of constantly checking things that's not going to have a match. So the solution, of course, is rather involving everybody who could possibly be involved, You only involve those that are definitely involved. This is what it was referred to as a directory. So the idea being is that rather than broadcasting this bus, hey, everybody, we're updating this cache line, instead of something called directory. The directory is going to track which caches have a copy of this cache line. And so what this means is you're actually going to have a directory for every cache line in the system. And I want to emphasize that so you have a cache line directory for every cache line in the system. And then you're going to trust that, of course, between your multi-core or even more often many-core system, you have a network to communicate between things. So there's been a lot of research over many years about how to best do coherence protocols with directories, and more importantly, how do you actually organize the directory itself. And I'll come back to some of these conversations in a few minutes, but the first order, we can take a very simplistic view and say that every possible cache line, not just the ones on chip, but every possible cache line, even in memory, has a directory. We'll go with that approximation for now. OK, so how does this work? Well, here we have our system we're working on. So it has 6 processors, 6 caches, a network. And notice what we've done. We put the directories near memory. And the reason why is this directory is kind of like a shared source for all of the memory transactions, right? And I'm sorry, I hate to pause. Did you just hand over a Plicker card? The student who just walked in and handed over a Plicker card to someone else, did you just swap cards? I'm sorry, I'm a little derailed because I saw you walk in and hand a Plicker card to your colleague. OK. OK, fine, good. Sorry. OK, so yes, so we put the directories at the memory controller. The reason why is the directory is associated with each cache line in memory and such. So there's no reason to have it be centralized. We can just instead put it near the memory it's going to be needed, right? So this directory controls all the memory associated with this memory. This directory associates with all the memory for here, right? So this way, we're already starting to get some parallel partitioning of our hardware, right? So it's not totally centralized. It's centralized at the point of memory controller. So anyone that needs to talk to this memory is also, of course, naturally along the way going to talk to the directory. And so it can see, who needs this data, who already has this data, et cetera. And so how does this actually play out? Well, inside these caches, each cache, of course, like before, has a tag and data. And we added a few bits in for coherence. So this is, in many ways, like the snooping case. But the additional part is rather than just having cache states for the caches, there's also on memory as well, as I said. So for each piece of memory, there's, of course, going to be the data, the directory, and the cache state associated with that. So as I said, there's many different directory protocols. The one we're talking about today is essentially, you can think of it as a approximation of MSI. So it's not even Mezi or Mosey, it's just MSI. So what does it look like? Well, there's 4 states for the directory. So one is, of course, invalid, which we're familiar with. It's not at all in this cache. So these are the states you see inside the cache side. There's states for the cache side and states for the directory side. So these are the ones for the cache. OK, so yeah, it's not there. Great. Shared, like shared before, meaning I have a copy. I'm not allowed to modify it. And the copy I have is the same as the one in memory. It's a clean copy. It's not dirty. OK. Modified. So this one is like the M state from before, right? So I have permission to write this data, and the data I have may be dirty. And then finally, there's a transient state. So I mentioned this for snooping. This is common, but for the course, you kind of could ignore it exists. For directories, the message delays really do add up. And so we do need to be conscious of the fact that it's in transition between different states. And so you're often going to put a request out and go into transient and then wait for someone to come back. So for example, we can imagine some common cases. Like let's say a processor does a read and it's a cache miss, and it's totally available. No one else is reading it, so it's going to start off in transient. Well, it's going to start off in invalid, go to transient, and then when the data comes back, it's going to go to shared. Okay, let's say you want to do a write to a miss that no one else is touching. Okay, well then it's going to be invalid originally. You're going to go to transient, and then you're going to go to modified. Okay, well what if you had a read miss to something that's shared? In that case, it's really simple. So in that case, you're going to put a request out. And depending on, so it's going to still go invalid to transient, you're going to end up in shared. Now the directory may need to do more work behind the scenes to make that happen, but you're going to go from invalid to transient to shared because you're asking for read access. And then likewise, if you want write access and this thing's already been shared by other people, you're going to start off invalid, go to transient, and you're going to go to modified. And then once again, the directory is going to figure out how to perform the right transactions to get you there. So what are the states the directory itself can be in? Well, once again, there's kind of 4, and these ones are a little bit different. So the most common one is this read state. And so in this read state, we're going to use the directory, and a directory is just a bit vector. So each bit represents one cache or processor. And so for every processor or cache, or every bit said in that directory, is somebody that currently has a shared copy of that data. So at this point, everyone who has that data, and it's not different from one in memory. Now, if some cache did request to modify the data, well, in that case, you're not going to use the directory because we're only letting a single cache modify it. So we're just going to retract the fact that it's in the right state and the ID of the single modifier, because there's only allowed to be one modifier. And then for these transient states, we're going to see this in a few seconds, where we have to have a little bit of waiting as we wait for everybody to acknowledge what's happening. We're going to send multiple messages out. There's a transient where I'm transitioning from read, or there's a transient state where I'm transitioning from write. And so that's why you need a directory or an ID in those cases. So it makes it easier if you do some examples. So we're just going to zoom in on one CPU doing these transactions. What's going to happen? Well, it's going to do a load. It's going to miss in the cache. So we're going to say, hey, I want to do a read. So I'm going to say I want to share request, send that to the directory. And so it's going to send this over to the network. And the network's going to know, based on the address, which directory controller to route it to. So then get to that directory controller. Directory controller is going to look up that address, look inside its directory. It's going to find out what the state of that line is. So in this case, the line state is R, meaning that nobody has a dirty copy. And they're not waiting for any other transactions to complete. And so it's a number of shares. So now I'm going to set the bit corresponding to the CPU that requested it in the directory. And we're going to send the data back across the network. So send a share response message. And then the shared response, of course, going to get routed over a network and then arrive at the cache. And now the cache is going to mark this as, it's in the coherent shared state. Have the data in the tag, and we're ready to continue to CPU.
So it seemed like one key difference here is that in the earlier model it was all autonomous, and the L1 cache was deciding for itself what state to be in based on replies. Whereas in this case, it's more that the upper level cache is being instructed by the directory controller what to do with the line.
That's a reasonable analogy. Yes, so if you want to think of it that way, that's fine. For coherence, you can think of it as, for snooping coherence, you're right, it's kind of a peer-to-peer thing. Based on information I've been exposed to on a shared medium, how can I infer the right combination of things to do? Versus in the directory, you're right, you were definitely trusting the directory to enforce things. In practice, because the caches can't take unilateral actions, you're trusting the directory to be an arbiter. So that notion of kind of being semi-centralized definitely is a good intuition. Once again, this is a simplistic directory protocol with essentially it's only the equivalent of MSI, and so you can imagine with more states and trying to reduce latency. You can see there's a lot of different message hops here. You could do things that are more clever, where if my neighboring cache does have a data, even though it's not quite snooping, they might be able to still find it out. So they might be able to forward the data rather than going all into memory. So for example, for the second. This is not needed for this course, but if the directory looks up and finds another core already has that data, rather than going to DRAM and back and say, hey, forward your data to this core who wants it, for example. So the directory can do some really cool optimizations that way. But for this course, we're kind of doing a very simplified protocol, because otherwise it's too hard to write out. Okay, and then for the case of doing writes, what's going to happen? Well, we have one CPU who wants to do a write, and it's going to have multiple people who have already been sharing that line in the read state. So it's going to go to the cache. It's going to miss. So now it wants exclusive access. It's an exclusive request. It's going to go across the network, get to the directory, and it's going to read the directory, and it's going to see, oh, wait, it's in the R state, meaning people are reading it, but there are people who are sharing it. OK, well, if people are sharing it, we actually need to invalidate their copies, much like we did with the MSI protocol. However, in this case, we need to explicitly send messages to them to tell them, hey, this particular cache line needs to be invalidated. So these invalidating requests go across the network, one for each cache. It's not a broadcast, right? They're being specifically sent to the people who are listed in the directory. It's going to receive those requests to invalidate. It's going to actually invalidate it. Then it's going to acknowledge that it invalidated it, send that message back across the network. That's going to come back to the directory. It's going to make sure that all of the invalidation acknowledgements have been received. So finally, when that entire directory is zeroed out, so this is in the TR state, that transient read state, leaving the transient read state. So when it's finally zeroed out, then it knows it's OK to go to the M state, or the W state, and it's going to tell the first core, yes, you now have exclusive access. Right? So now it's going to say there's no more sharers. You now can have this data exclusively, and then it can do its store. So you can, as I kind of alluded to a few minutes ago, this can generate quite a few messages. So this may sound inefficient, but hopefully the way your code is written, this happens rarely, right? Number one, hopefully you have less cache misses. Number two, amongst the cache misses, hopefully they're producing less traffic on the network, because otherwise that's going to be a lot of overhead. Question?
In step 2 there, that miss is because they don't already have exclusive, right?
Yeah, the data is not in the cache. Yeah, so exactly right. OK, yeah. So in the beginning of the lecture, I was saying how you can call that an upgrade rather than a miss. For my own personal vernacular, I tend to use the word miss when the data is not there. OK. So this is kind of a flavor of directories. Like I said, there's a lot of optimizations you may want to consider when implementing one. So the first thing that stands out at you is the fact that, wait, if I have to have a directory for every potential cache line, that could be a lot of overhead, right? Because I only have a small amount of data of my entire system on the on-chip caches versus in memory. So if I have to have a directory for everything that's in memory, that's going to be bigger than the cache, right? And so the first observation you might realize is, wait, maybe I should keep the directory information in a cache, right? Some sort of directory of cache information rather than keeping it all on chip at once. But even that can be very big. And so there's some ways to make it smaller. One of the problems is that you may have a bit vector where each of these represents a different core. and let's say it goes like 1024. If you have 1,000 cores, having a 1024-bit bit vector is a lot of overhead. So there's been a lot of research on these kind of problems. And so one solution is observed that in practice you only have a handful of caches using a thing. So you use a handful of these are 1 bit wide. That's not clear. I'll just mark them as all as 1 bit. Versus here, maybe make these 10 bit wide, and you hold the ID, right? So you can say core ID. And if you only have, let's say, room for, let's say, 4 cores, and if they're all full, then you broadcast. And so even though you don't have a broadcast bus, you just send a message to everybody, right? So that handles most cases. In the cases it doesn't handle, of course, you have that broadcast. There's been a zillion different optimizations like this in research. But let's say the first order for this course, you can imagine it just as this simple bit vector. And you can imagine that there's one associated for every cache line, potentially. And if need be, they'll come on the chip. But that, restore off chip. But that detail we can kind of hide. OK, so when it comes to implementing these, what's going to happen? Well, we just showed one transaction in flight. But if you have a lot of cores and you all want to run them in parallel, you need to have multiple transactions in flight. Notice back to our Little's law, having more parallels and we get more things in flight for more throughput. So this is where it gets really hard to get your things correct as a processor designer. Unfortunately, in the modern era, of course, that most applications require multiple cores. So this is a challenge your design team will have to overcome. And especially, it gets even more interesting when you have not just multiple transactions in flight, but multiple transactions in flight to the same cache line. OK, so let's just give you a flavor of the challenges. And then kind of wrapping up coherency. So we've talked about the point of cache coherence to make sure that, as it says here, every store to a memory is eventually visible to all loads to the same address, right? So every cache has the same value for a single address. And so we showed you 3 protocols, MSI, MESI, and MOSI. Those are all kind of snooping based. And then, OK, well, what's the difference between snooping and directories? Well, snooping, we assume we have this broadcast medium on a bus. And based on what we see and the occasion transactions we perform, we can get to the right state. Versus directories, we now have this directory that keeps kind of a centralized status and then sends single messages to those who need to be involved. In terms of the trade-offs, snooping is definitely lower latency, right? You can see that if the data is going by, you can grab it right away. You can change right away. There's typically fewer message hops involved. But the penalty, of course, is that snooping. That bus really takes a lot of overhead, a lot of energy, and it's not very scalable. So that's why, of course, we have directories. Let's go to higher core counts, and they're more efficient with their bandwidth. But the penalty is you may have to have more hops. OK, any coherency questions? Let's do peer instruction then. So you're on a system that's using the MOSI protocol, and you decide false sharing is problematic for your code's performance. So you have some ideas about how might you reduce false sharing. So in this case, I'm asking which of the following will not reduce the number of false sharing. Would it be reducing the cache line size, rearranging your data for your application, adding more threads to the application using more cores, or none of the above? So think that one over for a second by yourself, and then we'll take a vote as a group. OK, why don't we vote now individually? Your finger is covering part of it. Yeah, there we go. Perfect. Great. OK. All right, why don't you talk to your neighbors? Okay, let's take a vote now if you're talking to your neighbors. Great. Great, okay. Oh, okay. Well, I'll share the voting results. So initially, a lot of weight towards C and D, and then similar. Okay, so no one was too persuasive today. Let's talk about these. Okay, well, if we have false sharing, that means our threads on different cores are accessing different words but in the same cache lines. So if we reduce the cache line size, A, that's going to, of course, reduce the odds of it happening, right? So that actually will reduce the number of false sharing. So it's not A. Good. Okay. What about B? What if I rearrange the data layout of my application? Well, I didn't specify how, but you can imagine if you have a problem with false sharing, if you arrange your data layout, you can move things farther apart such that you don't have different threads banging on the same cache line. So that will also reduce the number of false sharing. So that's B. So B is okay. So B will reduce the number of false sharing, and thus it's not the answer for this peer instruction question. C, what if I just try adding more threads? That probably won't make it better. If anything, it might make it worse, depending on your application, right? So this is the one that actually you should be conscious of, right? So yeah, I mean, if you have a problem with false sharing, in practice, you've already built the system, so you're not going to do A. C is not going to help you, so really B is the one you want to do, right? So when you're doing parallel programming, you should be conscious this happening. This happens more often than you might think. It's very easy when you're programming to say, oh, I'm going to, like for example, if you're using C and OpenMP, you're going to say, okay, I want my thread ID. So I believe it's something like, I think it's something like OMP gets thread ID, but someone might know the right API by memory. Okay, so now you have your thread ID number. And then what are you going to do? Then you go look in some array like that. That's going to cause false sharing, right? Because that means every thread is going to be accessing adjacent cache lines. This is a very common thing people do in parallel code. It's going to cause false sharing. So for example, if you rearrange your data such that rather than it being, thread 1, thread 2, thread 3, even if you just space things out, where it's thread 1, this may seem space inefficient, but for not causing false sharing, this is going to improve your code. And so you should be conscious of that. Now, of course, if all these threads are just reading, there's no problem, right? But once they start writing, this is going to occur. So false sharing, I would say, is probably the most common source of poor speed-ups for parallel codes. Now that you've taken this architecture course, hopefully you guys can appreciate behind the scenes what's happening and causing that, and take interventions to avoid it. Question?
Does adding more threads cause true sharing misses, not false ones?
I guess I should argue that C is a bit ambiguous, right? Because it's not clear how these threads are going to interact with the application. It could be the case that with more threads, you're not going to increase the amount of data in the application. So there's going to be more interactions between cores. Now, it could be the case, as you suggested, that perhaps data that before was accessed independently is now going to be accessed, and so that could cause true sharing. Oh, okay. Actually, I can imagine that being a way to reduce. If you convert false misses into true misses, okay, in that case, I will buy C, and for that rationale. The thought would have been that more threads naively could have just increased the amount of sharing in general, which could cause both more true and false sharing. But the analogy you're describing, where what if it causes most of those false sharing cases to become true sharing cases? Yeah, in that case, I guess I could see C being the correct answer too. Oh, sorry. Yeah. Oh, sorry. C becoming a valid way to reduce false sharing, thus making D the right answer, I guess, technically.
Yeah, I had another objection to C. I don't think C is the right answer either, but for a different reason. I mean, I think if the question is saying which of the following will not reduce the number of false sharing misses, you're also saying which of the following guarantee to increase the number of false sharings. And adding more threads to the application could change the behavior of the thread arbitration in a way that's positive. You don't know, because you have no idea what the thread application behavior is going to be like. So, in my opinion, C was kind of 50-50. It might improve it, it might not improve it, probably won't improve it, but it certainly will not improve it. You can't guarantee that add threads is going to not work, so that's why I chose D.
Yeah, I think that's a good rationale. As you've seen throughout this quarter, some of these pre-instruction questions are more negotiable than others, and I would consider that a reasonable negotiation of that response. The nice part about pure instruction is you're not, of course, being graded on the right answer, because sometimes there's not a single right answer, and I'd rather have these conversations rather than the first round everyone get 95% of it right. So yeah, I think that's fair. I think the biggest issue, just the way it's phrased, is C is really ambiguous, right? And I think the logic in terms of any versus all, which you're describing about in terms of the logic for the whole question as a whole, that's also a concern. But I'm glad we had this conversation. We had a chance to talk about all the different possible nuances. Great. Okay, so we're going to shift gears and build on top of coherency and do something called consistency. And it's kind of hard to do consistency on its own, so we're going to mix synchronization. So we've now talked about how to get all cores agreeing they see the same value for a single word of memory. But now we're talking about, well, what order do these updates become visible? And so to build our way into that, we're going to talk about what happens when threads try to interact. And so synchronization is that process of multiple parallel entities interacting. And there's really two classic types of interaction. Number one is producer-consumer, where one thread or core is producing things, and the other thread or core is consuming those things. The other one, of course, is when two threads are both contending for a shared resource. And that's mutual exclusion. So both cases are common. And realize this can happen even in a single core system. If you have a single core system, but multiple threads or multiple processes, these things can still arise. Right? So let's go through it, right? So let's start off with that producer-consumer case. So in a producer-consumer case, what are we going to do? Well, we have one thread or processor being a producer, one thread or processor being a consumer. And what are they going to do? Well, we're going to have a really simple protocol. We're going to have this register. It's only have a buffer size of 1. Or it's actually a register, sorry, place in memory. Producer is going to write a word to that memory. Oops, there we go. Producer is going to write a word to that memory. And it's going to set the flag and let someone else there. So the protocol is going to be, if flag is 0, there's no new data available. If flag is 1, data is available, right? So we can see on the producing processor, what's it going to do? It's going to write the data first, store the data first. Then it's going to get a 1 and write a 1 to the flag. The consumer is going to busy wait, right? It's going to check that flag. And if it's 0, meaning there's no new data there, it's going to keep spinning. And then when it sees a 1, it'll pull the data out. OK. Seems straightforward enough. Is this right? Or maybe we should ask another question. Is there a way this could go wrong? If so, how?
So if the producer tries to write twice, he has no way to know that the consumers consumed the intervening data.
Correct, you're right. So this particular protocol does not have a way to apply back pressure or multiple things in flight. Okay, let's assume we're only just transferring a single word once.
How does it know when to do the one?
Which core?
The first one.
So the protocol we've established is the consumer will know the data is there when the flag is set, that one, right? So the reason why we set things in this order is we want to make sure data is there before the one is there. Other ideas how this might go wrong? Go ahead.
Out of our processing.
Sure. Can you elaborate?
So you could, the branch equals for instance, like the simple case is the branch equals goes forward before the one is written to flag, and it says that it's true, that zero incorrectly, because by the time that it would go to load the data, that it would be, the data should be there because the flag would be one at that point. But obviously the problematic case is if the instruction to write to flag goes forward and writes one before the entire store has happened.
Which is the entire store?
The store of data.
Yeah. Okay. So that's right. So the issue here is that it's extremely normal for programmers to expect for these lines to have gone in order. And as just explained, with our out-of-order cores, with our coherence protocols, and even just our store buffers, we might have slipped up in presenting the abstraction. So the issue here is coherency is going to guarantee that these two cores don't have different values for X data or X flag, but it's not going to guarantee which order those updates are visible. So we're going to get more into that in just a second, right? So the point is consistency, right? So a sequential ISA tells you how processor sees its own memory and data in the program order. Now, memory consistency, often specified in the model, describes how we view data in terms of loads and the corresponding stores. So the contrast these two terms because they're very related, but in this case we want to be distinguishing. Coherence is about a single address, right? We keep talking about, okay, how is this single cache line being maintained coherent? Consistency is a property across the entire set of memory space. So I'm going to wrap up just by showing the example where this can go wrong. So initially we have flag equals 0, right? But the question is, that's assuming that when flag goes to 0 to 1 from the point of view of the consuming processor, when that transition is visible, the data has already been written, right? But as alluded to, perhaps because of a store buffer or something else, maybe data is not there yet. So this slide is kind of saying, what happens if the consumer sees a flag of 1, but data is actually not there? That's how we can get the wrong answer. So the ideal memory consistency model